Good morning, everyone. Today you're going to study transient and dynamics. In the last few lectures, we studied different DC and AC motors, and all the analysis we did was in a steady state. Today you're going to see a little bit of a transient and dynamics, and to study transient and dynamics in electric machines, you're going to use generators and the DC motors. We're going to limit our analysis to that. The transient and dynamics in AC machines is relatively complicated, and it goes beyond the scope of this course. So for us, understanding DC machines in the context of generators and DC motors will be enough. This is a simple lecture, and then we're going to do some exercises. So by the end of this lecture, you should be able to model a DC generator as a motor and analyze the transient response, and model the disturbance or the changes in the internal working of the machine when an external disturbance is applied to it. As I said, it's relatively simple. We are going to use a lot of things that we saw in control systems and just apply here to model the machine again and then analyze the dynamics instead of a steady state. There are many applications of this, of course, because the analysis that we did was in a steady state, but to get to a steady state, we need to pass through a transient. There is no way around. So how does a sudden change in an electrical charge in a generator, for example, affect the torque response of that generator? If apply a charge to an open circuit generator, it will draw a current, and if there is a current, there is a torque, which means that whatever source is we are using to power that generator will now experience a reaction torque that depends on the load we apply to it. This is a big synchronous motor that is used for power generation. What happens if a sudden change in the load is applied to the motor? It could lose synchrony and could lead to internal transients. Oh, that's another question that we could ask ourselves. So as I said, for today's lecture, we're going to do to focus on two specific types of machines. We're going to look at DC machines operating as a generator and as a motor. So let's start with the DC generator transient. The generator in a DC, we're going to consider the what it could call here an alternator. We have an armature winding that in the case of a DC motor would be power externally with voltage, but as when it's used as a generator, we have an input that is a power given to the mechanical part to rotate the rotor. The rotor in this case has a field winding with an external power supply instead of a permanent magnet. This creates the magnetization in the core. We are now rotating that magnetic flux using an external source, and that creates an induced EMF in the rotor. Sorry, in the stator, the induced EMF in the stator. This induced EMF now is the power source in the generator. If you consider the inductance of the coil and the resistance of that coil winding, and it has a current through it, there will be a voltage drop across L and R, and the net voltage coming out of the generator is then the output voltage, the output power, the electrical power that is coming from the generator. To do this analysis, we are going to use a few assumptions. The first one, is that there is no magnetic saturation. And by saying that there is no magnetic saturation, we can say that the inductance of these coils do not depend on the current. If there is no magnetic saturation, the inductance of the coils do not depend on the current. Does that statement make sense to you? Let me ask you this, why would the inductance depend on the current? Can anybody explain that?
Can you say that again?
Why would the inductance depend on the current?
I mean, back when we did I think it was like magnetic machines or something. If you subjected like a magnetic core or something to some sort of voltage and created a current, you would create a flux through that thing, and that flux would be. Now I'm lost. I think I was on the right track.
You're on the right track, yes. So the inductance, I see where you want to get. The inductance is defined as the number of turns divided by the reluctance. If you apply a magnetic flux, you develop a magnetic flux in the core that is too high. Now the inductance, the reluctance will change. You will start to saturate because the permeability of the core becomes non-linear anymore. So the greater now the current, the more saturation occurs in the core, the greater the reluctance. The greater the reluctance as you keep increasing the current, and hence the inductance will change. Now, because you're saturating the core, we are changing the reluctance of the core as we increase the current. Right. So you were indeed on the right track. And the other assumption that we're going to make here is that there is no mutual inductance. We're going to assume that the fluxes from the stator and the rotor operate at a different axis, and there is no mutual inductance between them. Under these two assumptions, we can now start to develop the equations, starting with the back EMF and the torque equations for this generator. We saw this for DC machines before, so these two first equations are not new. We have a constant that depends on the characteristics of the motor, pi, number of turns, if you remember. Phi is the magnetic flux, and omega is the speed. That's for the back EMF, and for the torque, we have the same equation, but now the torque depends on the current instead of the voltage of the speed. So this would work well for a DC motor, assuming that we have poles, we have magnets, right? So everything here would be fixed. In case we replace the magnet with a coil, now we need to take into account the current and through that coil. So we could rewrite these two equations under the assumption that, again, there is no magnetic saturation and there is no mutual inductance, that now the back EMF, instead of depending on K, a constant, and the flux, will depend on the field current, the current that passes through the rotor coil. And then, of course, if that is the case, our constant will change. So Ka is now Kf is a different constant times the strength of the current through the rotor winding, and also depending on the speed. So this makes perfect sense. The greater the speed, the greater the EMF, the greater the current, the greater the EMF induced, the stronger the magnet would be in the rotor core. And you could say the same for the torque. Now the torque depends on Kf times If, the current, and the current now on both the stator and the rotor side. All right. Okay, now it's the easy part. Now that we have made these assumptions and we have established the equations for torque and the EMF, we can look at the field circuit and develop an equation for the transient of this circuit. So this is very simple. This is a first order differential equation. So let's assume that the machine is rotating at a given speed, and then the switch in the rotor core is closed at a given time. How can you model this? Well, we can do Kirchhoff's law for the rotor winding, and we have the input voltage being the voltage drop across all elements in the circuit. Nothing new here. RF is the resistance, LF is the inductance, and IF is the current. You can take the Laplace transform of this equation to help us solve it, and doing the Laplace transform for no initial conditions or zero initial conditions gives us the second equation, which, following some simple manipulation, can be written as this. And then now if we divide everything by RF, we can create tau F, the torque constant, LF divided by RF. This is the torque, it's not the torque constant, the time constant of the field winding. And we can finally have equation 1 as the transfer function between the voltage applied to the rotor winding and the current developed in the rotor winding. Tau F is the torque constant for this field winding. And this is generally very high. In the order, it could be up to 2 seconds. There's a lot of turns in the magnetic core, so the inductance is typically very high, and the time constant is in fact can be close to 2 seconds, which is relatively high for an electric circuit. Okay, so that's it. That's a simple equation for the rotor. I don't think there's any mystery here. All right, we just wrote that a bit differently using the time constant instead of the original formulation there. Okay. All right, now that we have that equation, we can combine this equation and develop an equation for the induced EMF. And as you saw before, this is just a constant. Now that we have the field winding current, we'll multiply that by a constant that will take into account the speed, and that will now give us the EMF induced in the stator. So let's do that then. We have our EMF as Kf times If times omega. And now let's create a new variable here, a new constant, because we know that the EMF will depend on both, on the speed, linearly on the speed. We can take the previous constant and now multiply that by the speed and create a new constant Kg, which is Kf times omega m. And simplify even further, saying that the EMF is now proportional to the field current. This operates at a given speed. We take the Laplace transform of that. We have the induced EMF as the product of the current times that a constant Kg in the frequency domain. We had now a transfer function for If. I'll remind you what it is. Here it is. We have If. Now we can isolate If from this equation and combine that with the previous transfer function to create now a transfer function between E and V. Right? Vf, the field voltage. We apply a voltage in the field winding that it gives us a voltage in the rotor. How do we do that? Well, we can simply factor I of f here, which is EA over Kg. Replace that in the previous transfer function, combine them, and this is what we have. The generated voltage to the field circuit voltage transfer function is that. So Kg, a constant, divided by the same transfer function we had before. Or we took the transfer function we had before, multiplied that by a constant, and that's the conversion from current to voltage. Remember that this operates at a given speed. Kg depends on the speed. If you change the speed, Kg will also change linearly, which is the nice part about this analysis, which again can only be done assuming that there is no saturation and no mutual inductance in the circuit. We can now look at the time domain. If we, as we assumed before, the input voltage was just closing the switch, this becomes a step function, which means that V of f is the magnitude of V of f divided by s. That's a step transfer function. That's a step that will add to the transfer function and then solve the inverse to get to these two equations here. A very typical equation that you are very familiar now. This is the step response of a first order transfer function. If you take the limit of EA of t when t tends to infinity, this gives Kg Vf over Rf, and this is what you're going to call the steady state voltage in the rotor winding. And EA is right there. Okay. Any questions here? So far, so good. Okay. It is very simple. To control systems, we dealt with things that were way more complicated than this. We can now represent this as a block diagram. We have the input voltage to the field winding. We pass that through its own transfer function. We get the field current. Field current times a constant gives the induced EMF in the stator. Okay. And that is pretty much it. Yeah. Okay. If you look here in this transfer function, this would be the steady state current. So the steady state current times Kg gives the steady state EMF. Okay, so when you apply a voltage, a step function, the induced EMF will follow this exponential curve and tend to the final value that we called capital EA. And now if we close the loop in the stator, in the rotor side, the current will also develop in the rotor side. All right. So that's for the circuit that is on the field, for the field winding, the circuit that is in the rotor. Now let's look what happens in the armature circuit, the stator circuit. Now that you know when you apply a voltage to the stator, when you apply voltage to the rotor, we have a induced EMF in the stator. We can connect the stator to a load and see and close that circuit to see what happens in the armature side. So here is the assumption you're going to make. We have two sets here. We have the characteristics of the winding itself, the reactance and the resistance of the winding, and we now have a load. So this here would be a load that we are trying to drive. And of course, we have the switch there that is closing once we reach steady state. So if this switch is closed when the rotation speed is constant, the EMF that was created here couldn't create any current because it was an open circuit. Now the circuit is closed, the current will develop. Now let's try to model this. Well, if this is the case, now the input to the circuit is EA, that's the voltage input, and is simply driving a LR circuit. So let's just do Kirchhoff's law for that. We have voltage drops across the resistors, voltage drops across all inductors. We can combine now all the resistors and all the inductors in one and call that the equivalent or the total resistance and the total reactance of the winding to simplify our equations. So it comes down to this simple equation here. The voltage drop across the resistors plus the voltage drop across the inductor, that is the EMF. And now we can solve for the current. So again, this is the total resistance, this is the total inductance, combining both the winding and the load. We can now take the Laplace transform of this. This is equation 2. Now we simply replaced IA here with the derivative of IA is IA of S times S, which allows us to create the transfer function between the current and the EMF. And here it is. And again, you're using the same artifact that here we are going to talk about in terms of torque constant. The torque constant is the total reluctance, the total inductance divided by the total resistance. That's the armature circuit time constant, which is typically much lower than the rotor time constant. If you're closing the switch, then from the stator's perspective, the voltage that we applied to it is a step function, which means that EA of S becomes the magnitude of EA divided by S. Replace that in equation 3, do the inverse Laplace transform, and that gives us an equation now for the current developed in the rotor, in the stator, sorry. This would be for a step input. Okay, tau AT is again the time constant. So what happens to the current? The current eventually settles at E over R, that is the steady state current, but it will get there following an exponential waveform. So now we have two equations. We have an equation for the current in the rotor. We have an equation for the induced EMF as well. We can combine them. So combine the two transfer functions we had, starting here. We can take this equation and replace the equation, the transfer function for EA that we found before. Where was that? That transfer function right here. Now we can solve for EA here and replace that into the new equation. So now we have a direct relation between V of F, that is the field voltage here, and the current developed in the rotor, in the stator right there. right, by simply combining these two equations. So let's see what we get here, and notice it's nothing complicated and nothing surprising. We're basically multiplying these two transfer functions, and when you multiply them, E will cancel out. It becomes an internal variable, and you have now current to, that is, stator current to field voltage. We have two times the time constant, the field and the armature time constants, that are constant that relates current to voltage again, and now the resistance of both windings will show here. Okay, and that's the final transfer function for the transient. If we apply a step voltage as we assumed in the beginning, Vf, which is now the input to our transfer function, is simply Vf over S. That's a step when you close the switch in the rotor winding. That's a step input. The current then becomes that times V of S times S, and to find the steady state value or the transient function, we need to do the inverse Laplace transform. And to do this, we need to expand that into partial fractions. So this requires three partial fractions, one for S, one for the field time constant, and one for the armature time constant. So we'll take the form of A over S plus B over S plus 1 divided by tau S plus A3 S plus 1 over tau AT. We can solve for that using partial fraction decomposition. I think we are all familiar with that now, so I'm going to skip how we find it. But here is the procedure. This is a simple partial fraction. So for A1, we go back here, we remove A and we set S, we remove S and we set S to 0, evaluate the transfer function. This is what we see. For A2, we do the same, but now we eliminate the other one would be that it will make this 0. So we set S to -1 over tau F, and we continue the development. That gives us A2, and we do the same for A3. Okay, so A on top of these equations is simply this constant here. Okay, any questions? So when you find these constants, we can finally do the inverse of equation 7. And when you do the inverse of equation 7, we see this. So what can we see in this equation? We see two important things. The current will have a steady state value, that is A1. And we have two transients, two exponentials, and that makes sense. One comes from the field winding, one comes from the rotor winding time response. Any questions? No? Okay. So you can now put all this into block diagrams to evaluate the final transfer function. We have the original expression here for the, we should say the original transfer function from Vf to Ea, that is the field voltage, the induced EMF. When you have the induced EMF, we pass that through the transfer function for the armature, and you get the current. You can also combine these two block diagrams in one and eliminate the internal variable like that. Okay. A1 would be the steady state armature current, which we can find by taking the limit, what the transfer of equation 8 when time tends to infinity, or we take the limit of S times that when S tends to 0. And that's what we get. Okay. And so we see here one more thing. You see that this time response kind of depends on two exponentials. It's not just one. You see the effect of both armature winding and rotor winding time constants there. And this is it. So this is just to acknowledge now that if you apply a voltage to the rotor winding, when you turn the motor on, the generator on, as it rotates at a given speed, the current in the rotor will develop, that creates an EMF that develops a EMF in the stator. The stator creates a current, and this entire transfer function I will have to overcome this 2 time constant. Okay, so this is it for a generator. Now we can look at this system from a different perspective and use it as a DC motor instead. So if there are no questions here for the generator part, we can move on to the motor part. Are there any questions? No? Okay. So if there are no questions, let's move on to a DC motor operating mode. So if you're looking at the DC motor, we need to explicitly highlight 2 components, the current and the speed, and assume now that the field winding is constant. So you see in the generator mode, the field winding could change, the field winding current or voltage could change, and the speed was set constant. Now that we operate as a motor, we want this to go the other way. We want the electrical characteristics of this circuit here to be fixed, and maybe the voltage to change, and maybe the speed to change, not the voltage. So all the voltage is here, all the current is fixed, and we want the torque and the speed of this motor to potentially change because it's operating as a motor. So our equations will have to change slightly, but that's fine because all we need to do is to create new constants. So let's do that for torque and the EMF. Now, same equation that we had before, Kf times I times If, but now let's combine If and Kf because If is constant into a new constant that you're going to call here Km. So we say that the torque is proportional to the current, and this proportionality constant is Km. Same goes for the speed, because Kf and If are supposedly constant when you operate as a motor. Let's put them in the same thing here and create an expression for the induced EMF, which now depends on the speed times a constant. Okay, so that's the new constant that we created. We can start by modeling the stator. Now we have the input voltage VT. You see, we had that was the output before, that now becomes the input, is the back EMF plus the current drop across the resistor plus the current drop across the inductor. And we can further calculate that, take the Laplace transform, factor out I of A, and create this expression that you recognize from control systems, with the only difference that a tau A here is L equivalent, or the total impedance the total inductance divided by the total resistance. Nothing new. Again, this is a constant that depends on the strength of the field winding current. So that's for the electrical part. We can move on to the mechanical part, and for the mechanical part, we can do the balance of torques. So to do the balance of torques, what can you do? We can say that the torque is proportional to the current. That's what we established before. And what is the torque? Well, the torque developed by the motor must be equal to all torques applied to the motor externally, or by the effect of friction and inertia. So this should have been, I think this is a small typo here. This is supposed to be J. So fix that in your lecture notes. It's supposed to be J. So the effect of inertia times acceleration, effects of friction times the speed, and the external torque, the load torque, TL. So using these 2 sets of equation, one for the electrical and one for the mechanical part, we can go back to the very same equations we had in lecture, I believe 13, when we first studied DC machines. And these are the same equations we got at that time. The only difference, once again, is that we are presenting the denominator in a different way just to highlight the mechanical and the electrical time constant. So the time constant for the mechanical part would be J over B, and the electrical time constant would be L over R. Right? And there is absolutely no difference compared to what we saw before. And of course, Km here is a constant that depends on the intensity of IF. So if IF changes, Km must also change. So these are the equations for the torque and for the current, or sorry, for the speed and for the current, or for torque and speed. We can put all that in a block diagram. Here is our block diagram. What do we see is different here? Nothing really. Simply again representing this as to highlight the time constants, and we see a different gain here. You see, this is our Km, which is Kf times If, and they are the same as we saw before. Okay, and here is the back EMF, EA. Okay. Now let's analyze this system in different operating scenarios that you may encounter when you drive them. The first scenario, the load torque is proportional to the speed. If the load torque is proportional to the speed, then basically our load consists of increasing viscous friction. So TL becomes proportional to the speed, BL times omega. And this adds now to the existing friction in the rotor. And you can now calculate the transfer function between the speed and position by rearranging the equations before. You've seen this, I think, 20 times in control systems, and we are probably still bothering you with this transfer function in this course. So I'm going to skip the development of this transfer function. You are all familiar with this. The only difference now, when we have a load torque that is proportional to the speed, this is basically increasing that viscous friction coefficient. And when you plot the time response, this is what we have for a step voltage input. We could have an underdamped, under or overdamped system depending on the balance between friction and inertia, a bit depending where the poles of this transfer function are located. So this is scenario one. A second scenario that we may encounter is when the armature inductance, which is typically the case for good motors, is negligible. If the armature inductance is negligible, then LAQ is 0, which means that the time constant of the armature is also 0. This means that a current will develop immediately as we apply EA. As a EMF develops, a current develops immediately. As VT is applied, the current develops immediately. Right? There's nothing else preventing the current from increasing. So if the armature inductance is negligible, then one of our poles disappears, and the transfer function now simplifies to this. So what is the time response for this one? Well, the time response simply depends now on the mechanical part of the motor. Right? So this is an assumption that we can make to simplify the analysis. It is, for a good motor, this is typically the case anyways. Another scenario that we could consider to simplify our life here is to assume that there is no friction. If there is no friction, we are simply driving an inertial load. And if that is the case, we can rearrange our equation to set B to 0 and simply add the inertial load to the inertia of the motor itself and recalculate the transfer function. Okay. And the fourth scenario is when you disconnect the power supply. So in this scenario, we assume that we have a voltage that will go from the input voltage that is established and is going to be set to 0. And when that is set to 0 at a time greater than 0 now, the speed is not 0. So the motor rotates, we turn off the power supply. What happens? If that's the case, then the torque immediately goes to 0. the applied torque by the motor immediately goes to zero. So the current, we are opening the circuit, so the current needs to become zero immediately. We can now equate the zero torque to the sum of all torques. This is all the torque developed in the motor, inertia plus friction, and that is now equal to zero because we set the input voltage to zero, we set the current to zero, the torque applied by the machine to this inertial and frictional load also becomes zero. So to solve for this, we can take the Laplace transform, but now when we take the Laplace transform, remember that the speed is not zero. There was anybody trying to ask a question there, or was that an accident? No questions. Okay, so I'll continue. So now the speed is non-zero, and you need to take that into account when taking the Laplace transform. In the Laplace transform, we see this negative omega zero in the initial conditions here. And now we can continue solve for the speed over time, and the speed over time will give us this, which makes perfect sense. When you take the inverse Laplace, that's what we have. So let's see what you get from this equation. This equation says that at time zero, the speed is zero, is omega zero, and as we turn it off, it will slowly decay following an exponential waveform to zero. And you notice that when time equals to zero, E of zero is 1, and the speed is indeed the speed at time zero. So the equation makes sense, and the equation then brings the current, the speed of the motor is slowly to zero until it stops. Okay, so those are the scenarios to consider. Are there any questions? No questions today? Anything in the chat? The chat is also very quiet. Okay. So hearing none, you can continue. This is simple. There's nothing really complicated about this lecture, I believe. So I see that to get students excited, to get you specifically excited, I need to give you something a bit complicated, right? Or nobody asks questions. All right, well, no questions. Let's move on then. I think you can skip the synchronous machine transient and the induction machine transients. These are just more for information, and I'll let you take a look at this later. For us, when you do our mechatronics projects, we are most likely be utilizing DC machines anyways. Okay, so let's do some exercises then, if there are no questions from you. Let's start with exercise 92. We have a separately excited DC generator driven at a rated speed when the field circuit voltage is suddenly applied to the field winding. Determine the armature generated voltage as a function of time, the steady state armature voltage, and the time required to raise the armature voltage to 90% of its steady state value. So this operates as a generator. We have the generator running at a constant speed. We close the switch. We want to know the EMF generated here, the equation for it, the steady state value, and how long it will take to reach 90% of the final value. Okay, is this the right one? Yeah. Okay. So let's do this example then. To start with A. And in A, we want to know the equation for the EMF as a function of time. So we can start by calculating the time constant. And because you're dealing with this part of the system just to EA, for now, this part can be neglected. Of course, the circuit is open, so there is no current developed here. The only time constant is this one. And the time constant there, we call that tau F, which is LF over RF. And in this case, that would be 25 ohms. You see how high the inductance is divided by 100, and this is also very high. So that tells you how many turns are in there, right? Quite a few to get you to 100 ohms. You must have a few kilometers of wire there, and 25 Henry as well. So this gives 0.25 seconds. The equation for the EMF is something that we calculated before. It was kg times Vf divided by Rf, 1 minus exponential of minus t over tau f. Now notice that this equation is the time response of the current to a unit step input. So it only works if you close the switch. So this it would be a step input. It is like applying 200 over S. So we get here, right? So this only works for a step input. So you have everything here. Kg is given is 100 volts per amp of the field winding. That's 100 divided times Vf, that is 200 divided by Rf, the resistance there, 100 times 1 minus exponential of negative t divided by tau f, 0.25, which is 200 times 1 minus exponential of minus 40 volts. So this answers question A, and the question B is, what is the steady state armature voltage? How do you calculate the steady state armature voltage?
Is it just the kgVF over RF?
Right, it's just this part here, right? Which we can also say is the limit of EA when time tends to infinity. So this is now the case to 0, and you're left with 200, which is indeed kg Vf over Rf. With this part here is the steady state current IF. It's not asked, it was just there for information. Okay, which in this case would be 2 amps, right? 2 amps. Any questions? Any questions? No? Okay. So hearing nothing, we'll move on. Everybody's tired. Yeah. Yeah.
The top circuit represents the stator side of the motor.
Yes, this is the stator, and this is the rotor side.
Okay, thank you.
Okay. So the next question is, what is the time required to raise the armature voltage to 90% of the steady state value? So how do we solve that?
Make it equal to 180 and solve for t.
Exactly. So we make, exactly. So we can take this equation here, and we want this, take this one, let's call this equation 1. We can take equation 1 here and say that we want the voltage to be 90% of the steady state value. The steady state value is 200 multiplied by 0.9 equals to 200 times 1 minus exponential of negative 40. So you can divide everything by 200, so this goes away. So you have 0.9 equals to that. We can move 0.1 to this side. We have 0.9 minus 1 equals to negative exponential negative 4t. This is negative 0.1 equals to negative that. So we take the sign away, 0.1 equals to exponential minus 4t. Take the natural log on both sides. Here, this side here we have negative 2.302, and this is equal to negative 4t. T equals to 0.75 seconds. This is the time it takes to reach 90% of the steady state value. Let me see what I prepared here. Let's do exercise 97. And then if we have time, we'll come back to the earlier ones. So I'll let you take a look at exercise 97 as I erase the whiteboard. So this is now a DC motor. So the equation, what it just did here was a generator. And for the DC motor, we have a slightly different condition. It operates at no load with 200 volts and a field wind current of 2 amps. Rotational losses are negligible, so register that information. Rotational losses are negligible. The rotor is intended to be stopped by plugging, that is, by reversal of its armature voltage. So we are going to reverse the voltage in the field winding to bring it to stop. Determine the no load speed, the expression for the speed after plugging, and the required time to stop. Right, so the motor rotates at 200 volts. In one direction, we're going to reverse that to negative 200 until it stops. Okay, so in the first question, we are interested in the no load speed. I'm going to call this omega 0, no load speed in the rotor winding. How can you calculate that? What are we given? We are given the Kf constant, we are given the If value. What can you calculate here? We could determine the constant Km, and the constant Km can be related to the induced EMF and the current. So let's see. We have Km, the motor constant. Km, the motor constant, is Kf times If. Kf is given as 1, and If is 2 amps, so this is 2. And now we can use Km here to relate that to the induced EMF, which is Km omega m. So this is the speed of the motor, this is the EMF, and this is the constant we just calculated. The question is, what is this? What is the induced EMF? What is the induced EMF in this case? And that's the key to answer this question. Let me remind you that we are calculating the no load speed, the no load speed, the steady state speed, and there are no rotational, all rotational losses are negligible. So that means we have no load and you have no friction. What is the torque developed by the motor?
Is it 0?
0. If the torque is 0, what is the current flowing through the rotor winding? This winding here.
Is it steady state current or does it?
The steady state current for a no load and no friction. Anybody? If we are driving no load and if you are driving no friction, there can't be any torque. If there is no torque, there can't be any current. So the current for a no load system is 0. So what is the EMF?
0.
Is it 0? Well, if the EMF is 0, then we have a current of 220 divided by 0.4.
That's 220.
It has to be 220. We need the EMF and the input voltage to be the same. That's the only way we can get 0 voltage, 0 current flowing through, because the net voltage would be 0. So this is because we have a no load system equals to VT, which is 220 volts. But this again is because friction is 0 and the load torque is 0. If we had friction, this wouldn't hold, because then the EMF would not balance the applied voltage. There would be a difference here, and there would be a current. And the current would then generate enough torque to overcome the effect of friction. So this only works for this specific example. And now we are good. We can calculate that. We know that using this equation, we have 220, which is VT, divided by Km, which is 2, determined there, equals to the speed. And the speed and no load is 110 radians per second. Are we good? Any questions? No questions? So I'm going to erase this because the next part will take more space. So if you want to ask me any questions about this part here, this is your opportunity.
Can you repeat the explanation again?
Which part?
Why current is 0?
Why is the current 0? Okay. So the current is 0 because we are driving no load and you're driving no friction. That means that there is no torque to drive. If there is no torque to drive, the motor cannot develop any torque. We always talk about torque, but torque only exists between two things. Torque is always driving something. It's like a force. You cannot develop a force if you don't have a reaction force. So you cannot develop a torque if you don't have a torque to drive. So the torque here must be 0. For the torque to be 0, and knowing that a torque is proportional to current, the current needs to be 0 as well. If the current is 0, then there is no voltage drop here, there is no voltage drop there. This voltage and that voltage must be the same, and hence we can come up with this equation. Is that better? Yeah.
Yeah.
Anybody else? No? Okay. So I will clean this. And then we are going to do question B, which is the expression for the current after we reverse the input voltage now to negative 220. Okay. So what do we say from this part of the example here is that we know that at a no load condition, the rotor rotates at 110 radians per second. Okay, so let's write that down. This is from part A. We had omega 0 as 110 radians per second. Now let's do part B. The speed as a function of time after which reverse the voltage of the rotor. So we can start by now looking at the armature voltage. So the armature voltage would be VT equals to the EMF plus IA RA. And this is equal to, what is the voltage here? The EMF is Km times omega m plus IA RA. All right, this is the input voltage. This is the back EMF as a function of speed. Just multiply that by a constant. And this is the voltage drop across the resistor. You notice that the inductance of the winding is considered to be 0. If it wasn't, then of course we'd have a third term here that would be L times di dt. What is the torque developed in the motor? The torque developed in the motor is Km times the current. And what is the torque now? We are no longer dealing with steady state. We are now dealing with a transient. We are rotating the mass, the inertia in one direction, and we're going to reverse that rotation direction. So there is friction. Sorry, there is no friction still, but now there is an inertial load to drive. So this is equal to J, the inertia, times d omega dt. Okay. From this equation, we can take IA. So just divide this by Km. And we can now replace IA in this expression here. That now gives us Vt as Km omega m plus J over Km d omega dt times Ra. All right. And what do we get now? Well, now we have most of the variables here. In fact, we have all the variables. We have Vt, we have Km, which is 2. We calculated that before. We have Ra, that is 0.4. What else we have? The inertia, which is 4.5. So we can replace all the values here. And you could even take the Laplace transform. So let's take the Laplace transform of this. What is the Laplace transform? That would be V of S equals to Km, that's 2 times omega. I'm just going to drop the subscript m here just for simplicity, plus this would be 0.4.5 divided by 2 times 0.4, that is 0.9, times the Laplace transform of the derivative of the speed. What is that Laplace transform? What is the Laplace transform of d omega dt? Omega s, and now we have initial condition minus omega 0, right? Because at this instant the motor is rotating. At this specific instant the motor is rotating. What is the voltage Vs here? What is the voltage V of S?
To 220.
Is it 220? Yeah, that's a step input though. All right, so it would be 220 divided by S. And of course with a negative sign, because we are reversing the voltage. What is this omega 0? This omega 0 is 110. That's what you calculated up there. So this is 110 right here. All right, that's we calculated in step 1. With this, we can solve for omega. We have omega here, omega there, and we have s there. So omega of s becomes negative 204.4 plus 110s divided by s times s plus 2.22 and so on. I was just rearranging this equation. We can now take the Laplace transform of this. This would take partial fraction decomposition. Now we have s over something here, s plus s over that. Sorry, a over s plus b over this. So this is just partial fraction decomposition. I'm going to skip that. Or you're going to get bored again. So let's just do the inverse Laplace transform right away in one step. The inverse Laplace transform, this is not showing very well. All the markers, they stop at the same time. The inverse Laplace transform gives omega of t as negative 110 plus 220 exponential of minus 2.22 t. Does this expression make sense? Well, let's see if the numbers make sense first of all. What is the speed at time 0?
Is it 110?
Is 110, right? And that's what you get here. If you set t to 0, this whole exponential of 0 is 1, negative 110 plus 220, 110. So that's an indication that at least we agree with that, right? Something easy that you can easily check during an exam, for example. Does my equation make sense? Do we get that for t equals to 0? Yes. So that's good. That doesn't mean that the whole thing is correct, but at least that part is. And now the next question is, how long does it take to stop? Time required for the motor to stop. How do we calculate that?
Set W to 0.
Yeah, we just set that to 0. That would be question C. Time for omega equals to 0. So take this equation. We have 0 equals to negative 110 plus 220 exponential of minus 2.22 t. So for t, well, this is simple. I think I can afford to skip this. 0.1315 seconds. That's how long it takes to stop. Of course, if it's not going to stop, it will just reach 0, and then you have to turn off, or you're just going to start spinning in the opposite direction. Any questions?
Yeah, could you explain how you got WS minus WO again?
Yes, so this is the Laplace transform of dt of omega, right? But this is for a initial condition omega 0, omega at time 0 is negative, is omega 0. Not omega 0, right? Like that. Right. So this Laplace transform for a non-initial condition would simply be omega times s, right? But because you have the initial condition, then you have to subtract the initial condition omega 0. That's where it comes from.
Okay, thank you.
Question?
Yep.
For the equation 220 over s equals to W plus 0.9, where did the 0.9 come from?
0.9 is J over Km times Ra.
Oh, okay. Thank you.
Any other questions? No?
Yeah, question?
Yeah, yeah.
So for all the scenarios we described, how would one know which one to apply to in terms of an example?
You need to analyze the example. I don't think there's a straight answer to that question. You really need to see in which conditions you're operating. But that's the best answer I can offer. Any other questions? No? Okay. So let's do exercise 94. Instead, we have here a generator, DC motor again, open circuit armature voltage of 220 volts when it runs at 2000 RPM with a field current of 1 amp. The motor drives a constant load, and then you have the load there, the inertia, and the motor and the load, and the armature terminals are connected to a 220 volts DC. The field current is 1 amp. Determine the expressions for the speed and armature current as a function of time. Okay, so we'll do that. In the meantime, as I finish to erase the whiteboard here, are there any questions regarding the design project report and design project presentation? No? Okay.
Just something that comes off the top of my mind if there's an opportunity to ask. Say that you find a better way to, I guess, perform a part of the simulation or something along those lines. It's due next Wednesday when we have to give in the report. But say you find a better way that would be easier for everyone to understand or better to present your point. Can you change that?
Yeah.
Okay.
Yeah, sure.
Just making sure. All right. Thanks.
Yeah. Yeah. So your presentation doesn't need to be exactly what you have on your paper. You could present things in a different way. You're not communicating information in the same way, so you can afford to have a presentation that it doesn't follow exactly the structure of your report. It doesn't need to be done that way. Okay, so let's do exercise 94. So I will let you read this one more time. So the back EMF, that's what you mean by armature voltage, is 220 volts when it runs at a 200 RPM with a field current of 1 amp. Given all the current situation here, we are driving a load of 25 Newton meters, the inertia of 2.5 kilogram per meter squared. The armature terminals are connected to a 220 volts DC source, and the field current of 1 amp. Determine the expression for the speed and the armature current as a function of time. So this also should be 220. There it is. All right, so let's start with this one. The important information that you have here is that when the motor is a open circuit and you turn when it operates as a motor as an open circuit, so nothing connected here, and then again this is 220. If you rotate at 2000 RPM with 1 amp here, we get an armature voltage of 220 volts there. What can we get with it? What is that information important? What can we get from it?
Means the torque is 0.
We know the torque is 0, yes, but what else can we deduct from that information? the motor constant, because you're giving a speed, we're giving intensity here, and they're giving this EMF. So based on all that, we can calculate the motor constant. We know that EA equals to Km times omega m. This is given for a given field intensity. So Km is simply 220 divided by the speed, which is 2000 RPM. So this 2 radians per second can be multiplied by 2 pi over 60. And this gives a constant of 105 volts per radians per second. Okay. And then we talk about in the example that when we now apply 220 volts here to drive a load, the field voltage, field current is also 1 amp. So this constant is still holds. Right? If this constant was obtained by at say 2 volts, 2 amps, it would have to be reduced by half now because we changed this to 1, right? But luckily, this was obtained for 1 amp, and the operating condition here will also take 1 amp. So this constant holds. So with that, we can use the same expression we had before from the previous example. Remember that we started with 2 equations, one for the electrical and one for the mechanical part, and that gave us an expression for VT, and that was EA plus RA times the inertia divided by Km, or I think I had Km here. Let's put it that way. This is from the last example. We just did it, so I'm just going to copy the expression here. The speed, the inertia times the acceleration. So the sum of all torques, that is inertia times the derivative of the speed, and plus the load torque that we are driving now. So this is the only addition to the equation we just developed. Then we have TMT here, which is the load torque, that is 25 Newton meters. This can be written as Km times omega and just rearrange the expression like that. So now we have everything. We have Km that we calculated here. The speed is what we want to solve for. RA is given, is 0.5. Km is the same. J is given, and T is given. So all here is known. We are solving for the speed. Solving for the speed here. And this is an input to our system. What is the input here? What is the input? Is 220 volts, and that's a step input. So we can replace this with 220 over S equals to 1.05 omega plus, I'll give you the constant that results from this, 1.19 omega S. So this includes J, RA, Km is 1.19. Taking the Laplace transform of omega dot is omega S, and plus the term that comes from this multiplication, which is a constant, that is going to be 11.9 over S. (11.9) Yes, over S, because when you take the Laplace transform, we have T. So the Laplace transform of a constant does just that divided by S here. And we can now solve for this. This is a simple equation. It's a simple first order equation to solve for. You know how to do this, right? I isolate for omega and do the inverse Laplace. So I think I can skip that whole part. This will be a simple equation. You don't even need partial fraction decomposition. So I'm going to skip some steps here and just give you the final value for omega of t, which is 198.2, 1 minus exponential of negative 0.0, sorry, 882 t radians per second. So that's the equation for the speed. What is the equation for the current? Well, the current, we can calculate that as the difference between the input voltage and the back EMF divided by R. Because this holds because the inductance is 0. And what is exactly the EMF? The EMF, we can replace that with the equation for the EMF that is a function of speed that we can get from here. So minus Km times omega of t divided by the resistance. And you can simply input this in the time domain there directly, and so for the current. So this is the expression for the current. So there's a lot of math steps here that I'm skipping, but I just want you to focus on the actual development. These math steps are trivial. I think you should, when you try this on your own, it should pose no problem. Okay, so we got an expression for the speed. Now, based on the expression we got from the last example, that this is where we started. Here's the speed. So for the inverse Laplace transform, that's what we get. And now we can input this in this expression. This expression is easy to manipulate and it makes sense. The voltage difference between this and that divided by R is the current. So this voltage here is a function of the speed, and I'll replace that speed into here. We can do everything in the time domain directly, and that gives us the expression for the current that settles at 23 amps, 23.8 amps as time tends to infinity. Okay, so that's that. This is the last example we're going to do today. In the next lecture, we're going to do a quick review for all the course contents as we prepare for the final examination that is approaching. And then in the following 3 lectures, we have the design project presentations. And again, I really encourage you to come and listen to your friends' presentation, because there's a lot of very interesting projects and that can give you a lot of good ideas for your future projects later. So do come to the presentations. We'll meet again on Monday for a review. And then after that, we have 3 sessions of presentations. Any questions, any comments before we wrap today's lecture up?
I have a question.
Yeah.
Could you please explain how you got 11.9 over S again?
Yeah, so 11.9 is the multiplication of this times t.
Isn't
This
it
times t.
1.19? Is that just the?
Did they make it? Is it 1 point? What is the numerical value here? RAKM times t.
You put 1.19 for the WS term, so I thought it would be the same for T.
1 point. No, because this one is multiplied by inertia, right? So this one is inertia times that times this. It's 1.19, unless I made a mistake in my calculations. And then RAKMT is 11.9. Regardless of what numerical value we are looking at, it should be T times RA divided by KM, should be this. And this one should be RAKM times J. Right? And
So
this
T
is now,
sorry, go ahead.
yeah, T is 25. This is the load torque.
Oh, so it's RA over KM times 25.
Yeah.
And they do a 1 over S.
Yes, and then when I took the Laplace transform, this is a constant. The Laplace transform becomes that divided by S.
Okay, I see. Thank you.
So this is 25 Newton meters.